everyone, to my session on the NVIDIA profiling tools, and good morning. I want to tell you a little bit about the NVIDIA profiling tools. I'm going to focus on the profiling tools. If you have questions about the debugging tools, I'm happy to answer them in the breakout session. Just one-on-one questions is fine. So what I'm going to do is provide a very brief presentation on the suite of NVIDIA profiling tools that are available. And then I want to do a demonstration of those tools on a set of hands-on exercises that I've selected. So my plan is that I'll tell you what the two tools are, Nsight Systems and Nsight Compute. And then I will start by demonstrating those tools on a hands-on example with a set of exercise steps. And then in the breakout session, if you join me, basically you can go ahead and finish those steps. So there's more steps that I can get through in the time that I have allotted to me, and that's intentional. The goal is to kind of set you up so you know how I think about using the tools and how I recommend that you use them. And then you can go ahead and complete the analysis exercise to get some practice on your own using those tools. The NVIDIA profiling tools family, we call the Nsight product family. And so it breaks down into two tools that are relevant for HPC developers, Nsight Systems and Nsight Compute. Nsight Systems allows you to analyze the performance of your application at the kind of system level. So the goal is to be able to get performance data on both the CPUs and the GPUs on your system, and then tell you something about the timeline of your application. So as a function of time, what was happening. And then that is important for understanding where your bottlenecks are that are unrelated to the GPU for the most part. And so the goal is you collect a timeline of your application and you see where your CPU activities are, where your GPU activities are. You know, on most platforms, GPUs are where the majority of the compute power is, and so you want to spend as much time on the GPU as possible. And so Nsight Systems helps you figure out when you're not spending time on GPUs, and then tells you also quite a bit of information about the GPU workloads themselves. But once you have made the majority of your application timeline run on the GPU, and you've removed bottlenecks like data transfers to and from a CPU, then you'll want to use Nsight Compute to dive in and do a detailed analysis of each of the kernels that run on the GPU, a kernel being individual discrete chunk of workload that runs on an NVIDIA GPU. Analyzing the performance of a particular kernel is, in large part, a kind of different exercise from analyzing the high-level application performance, and that's why we've chosen to break this out into two tools. However, there is a fair amount of overlap between the two exercises, and so both tools have some level of information about the corresponding application and also kernel level scope. Of course, there's also Nsight graphics for graphics workloads, but I'm going to assume that that's not relevant for this audience. So what Nsight Systems does is it gives you an application timeline. So time is increasing from left to right here, and it's giving you a trace of what's happening. So it's basically telling you the start and end timestamps of various kinds of activities that are happening. It largely breaks up your view into a CPU section and a GPU section. And I will do a demo of this because I know that the screenshot is pretty hard to read. But you basically have timestamps and horizontal bars that show you where various activities are happening. So you get to see information about where your compute workloads are happening on the GPU, that is kernels, where memory transfers to and from the GPU are happening, and also information that's happening on the CPU side, like the APIs that are used to launch GPU workload, but also traces sampling of the CPU itself, so you can get information on where the CPU threads are and what their workload is. This tool is useful for any application that's running on an NVIDIA GPU. So all of the programming models that target NVIDIA GPUs use the same underlying machine code that are generated, and in some sense can be said to all use CUDA under the hood, depending on how you define CUDA. And so our tools are pretty agnostic to the programming model that you use. So you could use CUDA C++ or CUDA Fortran, direct-to-base models like OpenAC or OpenMP. Obviously, like C++ abstraction layers like Cocos and Raja that sit on top of CUDA are also eligible. And so we're pretty agnostic to what programming model you use and can give you useful information regardless of the programming model. There's a couple different ways to use Nsight Systems. You can either drive the application with the user interface or at the command line. Because the command line method is more common in the HPC context on a cluster, that's what I'm going to focus on in my demo. And so the command line name of this tool is nsys. And then you can do NSYS profile and then the name of your application to collect a report, the timeline of your application. That is used for collecting it. And then you can either get some information at the command line. That's what that --stats equals true flag means. Or you can then download the report to your local system and then open it up in the user interface. And I'll show examples of both. Nsight Compute is our kernel level profiler. So the idea is you target a particular GPU kernel that you want to understand the performance of, and you want to then get some information about how you might both what the current performance of that kernel is, and then what steps you might take to optimize that kernel to make it faster. Nsight Compute breaks its analysis up into several different sections of analysis, each targeting a different kind of information. So for example, the first section that you're presented is called the speed of light section, and it tells you just very high level, what percentage of the memory subsystem am I using? What percentage of the compute subsystem am I using relative to the peak possible throughput of those things? Can generate a roofline chart like Kevin was just talking about to get a sense of where you are relative to the peak possible performance, and then give you some tips on what to do to improve it. However, any expert system in a tool is always going to have the limitation that it hasn't encountered every scenario, and it is limited to a kind of automatic analysis. And so it does pay off to get practice using the tool and understanding how to connect the information it's giving you to actual application, real kernels and applications. And so I'm going to try to give you a flavor of that. There's other sections. I'll mention a couple of them in my demo, but the speed of light section is usually the place you start because it tells you relative to the speed of light, that is the fastest possible performance of the kernel, how far did you get, how fast did you get? Nsight Compute is also fairly customizable with a Python-based system for setting up your own rules and analysis if you care to do that level of detailed analysis. Again, you can either drive the application through the user interface or the command line. My demo will use the command line, and the command line name of this tool is NCU, and then use NCU in the name of your application to collect a report. Now, one thing that is worth saying explicitly about Nsight Compute is that kernel profiling analysis in basically any tool that I'm aware of is pretty expensive because I think all of the GPUs that exist today, or at least the ones I'm familiar with, certainly the NVIDIA GPUs, cannot collect an arbitrarily large number of performance analysis metrics in one run of your application. There's just too many to go to get through, and the hardware can only support so many. So the way that we collect information is that we run your kernel many times in a row to collect all the statistics that we need to give you a comprehensive report. But then the flip side of that is that it makes your application a lot more expensive to run because every kernel is collected 20 to as many as 100 times to collect all the statistics that we need. And so you can get 2 orders of magnitude slowdown in your application if you try to profile every kernel. So typically what I recommend is targeting your analysis to a particular kernel that you've identified as a hotspot. And you may even want to go through that and only collect like a few instances of that kernel to limit the time it takes to collect the information. And so I'll be using that best practice in my demo where I'll be looking at an application where I don't expect the performance of the kernel to change too much from run to run, from kernel iteration to iteration. And so I'll just profile like one instance of it, for example, and focus on that rather than try to collect a profile in every single instance of the kernel. I've left here in this PDF, which is in the box folder, just some links to other information that you can get online about these tools. So the product pages are available, and they link to the documentation for these tools, and also a couple of developer blogs we've written on how to use these tools are available, as well as more in-depth training sessions we did for OLCF last year that I can link to. So I'm just going to leave those there for you to look at your own time. But what I wanted to do next is do a demo of how I think about using these tools. Feel free to ask any questions at the moment if you have them. Otherwise, I will just dive into that demo. So the demo that I've chosen to work on is an extremely simple application that just does Jacobi iteration. So you may have seen this in toy examples before. It's just a super simple application motif. And so I have some details written down here if you're not familiar with this algorithm. But the idea is basically that we are chopping up space into some number of discretized locations, and then we're solving some physical equation on those discretized points in space. The actual application that equation that we're solving ends up looking like some scalar field that is evaluated at various points, and then we create a stencil that evaluates that scalar field at some point in its neighboring values. And then we end up having an algorithm where basically, this is the pseudocode that explains what we're trying to solve. It says we're going to iterate until our error is smaller than some tolerance. And then we're going to loop over all of the zones in a two-dimensional spatial domain, and then set a new value of our scalar field f at the two-dimensional indices I and j as an arithmetic average of 4 neighboring zones at I+1, I-1, and j+1, j-1. And then we can compute an error as the difference between the new value and the old value. So that's what I've shown here, the square of that difference. And then we just keep going until that difference between the new value and the old value has become sufficiently small. Therefore, we have converged. And so I'm not going to spend much time talking about the algorithm. I'm more interested in how you would use tools to address a general problem like this. And what I've done is prepared a set of 9 steps that take you through a kind of methodical process of how I would go about taking this CPU application and then porting it over to run in the GPU. And then at each step, kind of giving you a sense of what you might do to improve that application. And I've set up some instructions here for how to do it on Theta GPU. I also have instructions for Ascent if you're using that system. Cori GPU, I didn't have time to set instructions for that, but it should be a pretty straightforward port from these directions. One thing I will say, though, is that both Nsight Systems and Nsight Compute are only supported starting from the relatively recent versions of NVIDIA GPUs. And so in particular, Nsight Compute is only supported starting from the Volta generation of GPUs, so V100 or the RTX 2080 type consumer GPUs. So I don't recommend using older GPUs. In particular, I don't recommend using Cooley for this, but Theta GPU or Ascent or Cori GPU or any other system with a Volta or Ampere class GPU would be fine for doing the hands-on exercises. So I'm going to step through these, the first few steps in this exercise on Theta GPU, and then we can talk about how I use the tools, and then you can follow up and complete these steps on your own in the breakout session. Okay, so let's take a look first at the code, just to get a sense of what's going on in this code. So it's I tried to keep it a fairly short C++ file, so you can see 131 lines, just C actually. And so here's main. Basically what we do is we allocate some memory for both the new value of f as well as the placeholder for the old value of f. We set up some initial data on the boundaries. In particular, this is initializing the boundary conditions on our two-dimensional domain. We have a while loop that just says while our error is bigger than some tolerance, like I was describing. And then inside this outer while loop, we do 2 steps in a row. First, we perform this iteration step. So that's this function Jacobi step. And this is the thing that does that average where we update the value at any given point by its neighbors. And then the second step is that we do a swap where we trade the data of the old value and the new value so that the new value becomes the old value for the next step. And then we check the error value accordingly. And so it's pretty simple while loop. We just do the Jacobi step and then the swap data step in a row many times until our error has converged. Jacobi step and swap data are these functions here. And so this is Jacobi step. This is doing that algorithm that I was describing before, where we're taking at any given index I, j, we're setting it equal to the arithmetic average of the 4 neighboring zones at these corresponding indices, and then we're computing the error. Again, this is just CPU code. There's nothing fancy about this. I'm sure many of you have seen code like this before. The swap data just basically loops over the entire domain and then sets the old value equal to new value. And then here's the allocate and initialize steps. Those are kind of less interesting or less relevant for what I want to talk about. But we set up some boundary conditions to make this an interesting problem. Okay, so our goal, the thing that we're going to do is we're going to profile the CPU version of the application and understand where the bottlenecks are. And then we are going to iteratively understand whether it's an appropriate application for running on GPUs. And if it's not, how do we go and rectify that situation? And then we're going to port some of the code to GPUs and then see how that affects the application profile. And then once we have the full workload on GPUs and the GPU kernels now become the bottleneck, then we'll talk about how to do kernel analysis on those kernels to understand how we would optimize those. I do want to step through that. And one thing that I will say is that, and I have some text here. I'm not going to go through all of the text to do this, but one thing that I want to say is that for this application that we're going to be looking at, you can probably just tell by inspection what the time is going to be spent on, right? It's super simple. There's really not a whole lot going on. You'll probably be able to guess where the time is being spent. So my goal is not to trick you, right, and claim that this is a tricky exercise. It's not. It's intended to be simple. I'm going to go through this methodically anyway, because my belief is that being methodical about it and having the same approach in general can help you so that you don't jump to mental conclusions that are not warranted by the situation. This is important because I think people, when they're beginner to intermediate GPU developers, assume that they understand or have learned something about the GPU architecture, and then therefore think that they have a sense of what's important to optimize, and then go and optimize that thing. But as good performance analysts, we should know not to make those kind of assumptions, but use the profiling tools anyway, even when we are relatively confident that we know what's going on, because it never hurts to double check your assumptions. And I can't tell you the number of times that I've heard from people using NVIDIA GPUs for the first time that they've heard things like, oh, divergence of threads on a GPU is bad, and if they see some divergence in a kernel, they should try to avoid that. And in practice, that may be a true statement, but whether or not that's the most important thing to focus on, you can only really know by collecting a profile and understanding the performance of the kernel. So please, if you think you know how GPUs work, collect a profile anyway, because you may be surprised about what's going on. And I am often surprised, even to date. I've been doing this for a while now. I'm still often surprised about what bottlenecks are in an application and what needs to be done to work around them. And they're often not in the places that you think. GPUs are not simple pieces of architecture. They require a different intuition than CPUs do. And while that's unfortunate, it makes it harder. It also is why we all have jobs as computational scientists. So let's dive in and look at this application. Okay, so the first thing I'm going to do is not just blindly put GPU code in, but first I'm going to understand where the time is being spent in this application. Now, if you collect a profile of this application within such systems, it can give you periodic samples of the CPU program stack, and so that's okay. That can be useful for understanding things. But you can do even better than that with a little bit of manual instrumentation of your code. You can instrument your code using an API called NVTX for NVIDIA Tools Extension, and it's really simple. Basically, what you do is you put this API NVTX range push with a string corresponding to some human readable name, and then NVTX range pop around some section of code that you care about. And so basically you're putting a profiling region on the stack, and then the string that you write here inside range push is what name the profiler will assign to the region of code in between the push and the pop. This is basically manually instrumenting your code, right? Manually marking off sections of code that you think are interesting and giving yourself a name so that when you look in the profiler, you understand what was happening in that section of code. Pretty straightforward to use. You just need to include the appropriate header and get the right library at link time. And the way that we're going to do this is to profile. So first of all, let me just run the application. I shouldn't jump ahead of myself. Let me just run the application just so you see what the output is like. So I have the compile and run instructions there. Oh, first I need to set up my environment. I have some steps here. On Theta GPU, it's actually pretty simple. You just need to set a couple environment variables that sets the location of CUDA and the architecture of the GPU that we have. Theta GPU is A100 GPUs. And so, right, let's go ahead and just compile and run the application with GCC. Again, this is, that bit is wrong. Sorry, that exercise's path is wrong. That's typo in the directions. It's just called jacobi.cpp, and then Jacobi. And yes, this repository is just on my GitHub. You can see where it is there. And J-Hook put a link to it in the track 6 breakout NVIDIA Slack channel if you are curious. Okay, so this is basically output. So we can see that this runs for a little more than 550 iterations. After every 25 iterations, I'm printing out what the error is, where the error is the difference between the old state and the new state. And so this application runs in about 0.02 seconds. Okay, so let's see what I did to add this instrumentation API to the application. So basically, you could see I'm adding NV tools ext.h. This is the header, and then just adding a bunch of ranges with strings that I have chosen to denote what's going on in the application. So in particular, I've added 5 profiling ranges or regions. I've added one for allocating the memory and then freeing the memory. I've added one for the step that initializes the data, and then ranges for the Jacobi update step and then the swap data step, right? So we can probably guess that this is where the bulk of the application time is. This is the thing we really kind of care about as computational scientists. But for completeness, it's important to profile everything that has non-trivial work, just so we are sure that we know what's going on here. So that's what I do. And then I can compile this code using the steps that I have here. Basically, I just need to point to the location where CUDA is available to get the appropriate header and library file. And then the right link line, which is just NV tools ext. And then I go ahead and compile the application with that. So you can see I'm using this new Jacobi step1.cpp, which is my first step. It has this instrumentation. Okay, now let's use Nsight Systems to collect the profile of this application. Now again, there's no GPU activity yet, right? We're just looking at CPU code. And so all we're trying to do is get a sense of where the time is being spent in the CPU code. So nsys is the name of the command line tool, and then profile is, I don't know if I can make this bigger. I don't actually know how to zoom in, so sorry. But if it's too small, let me know. I can try to make it bigger. So nsys is the name of the command line tool, and this is just in your path by default on Theta GPU. On most systems, if you do module load CUDA, it'll come as packaged with it. And then some systems like Summit and Ascent, there's actually a separate module for it that you can also load, module load Nsight-systems. Let me see if I can make it a little bit bigger. Appearance. Does that work? I don't know if it actually did anything. Anyway, sorry about that. The nsys profile is the sub option that we care about. So basically, it will only, like, this is the one we care about, just nsys profile. And and then --stats equals true is what allows us to collect some standard out at the end of the application that gives us a summary of what happened. Let's go ahead and run this. Okay, so we get the output from our application. We see it still took about 0.2 seconds, so this doesn't really add a whole lot of overhead to use this. And then Nsight Systems gives us a set of summary sections or analysis standard out sections that give us different kind of summaries of what happened in the application. This is what that --stats equals true gives you. And what we do is we get this NVTX statistics section. And so basically what this does is it summarizes each of the NVTX regions that I just added to my code, and then it sums up the time spent in each of these. And so we get a fraction of the time as a function of all of these NVTX regions, and then also some like raw time in nanoseconds, and then like average, minimum, and maximum if you want statistics on individual on the individual kernel implications. So like on average, each of these Jacobi updates took about 26 microseconds to run on the CPU. And so we can see that as we kind of predicted, Jacobi update step and the swap data step are where the vast majority of the time is spent, right? This initialize, allocate, and free steps are basically negligible, how much time is spent there. Now, you can load this into the Nsight Systems user interface. And so what you can do is, basically what I'm going to do is I'm going to SCP this QD rep file. So this is like a report file that's generated. You can download that and bring it to your local system. So like if I SCP this from Theta to my local system, then now I have this Jacobi step1.qd rep on my local system, like so. And then what I can do is I can open up the Nsight Systems user interface and then load that in. And so this is the Nsight Systems user interface is pretty boring. Before you load a report, and then you would go to File and then Open, and then you would then locate that file on your file system and then load it in. This tool, both Nsight Systems and Nsight Compute, are freely available, and so you can go and download them. All you need is an NVIDIA Developer Zone account. So I'm going to find that Jacobi step1.qd rep and open it up. You can just ignore this error that it shows you here. What we're just going to look at is this NVTX row. So you see we get a row called NVTX, and these are the ranges that we manually added to the application. Now, almost all of the application is in a pretty short timeline here, and so it's pretty hard to see anything. What you can do, though, is zoom in, for example, by holding down Control and scrolling in your mouse wheel, or like a pinch and zoom motion if you're on a touchpad. So if you zoom in far enough, you'll see these individual regions. And so basically, the vast majority of the time is spent iterating between Jacobi step and then swap data. And each one of these shows you the duration and time of each region, right? So each Jacobi step is about 26 microseconds, like we saw from the output. Okay, so I went through this because now we want to see what happens when I start adding GPU work to this application. So let's go back to our application and look at what step 2 is. So in step 2, what I'm going to do is I'm going to allocate the memory with CUDA managed memory. So CUDA managed memory is memory that can be accessed on either the CPU or the GPU, and will dynamically migrate to where it's used. So if it's on the CPU and then you access it on the GPU, it will automatically migrate from the CPU to the GPU. So that's a super handy thing when you're first doing your port to CUDA, because it allows you to really not spend so much time thinking about the memory motion, spending more time getting offload done initially, which is the right thing to focus on. And then later, if data transfer is still a bottleneck, you can then optimize that. But it really takes the effort away from thinking too much about data motion while you focus on writing your initial GPU port. I'm going to use CUDA-C for this example, but like I said, none of what I'm talking about here is specific to CUDA. You could use OpenACC or OpenMP, or Cocos or Raja, or other high-level programming models if you wanted to. It also would work with Fortran. So basically, we just replace our calls to malloc with this call CUDA malloc managed. Again, this is not a CUDA tutorial, so I'm just going to tell you that what this does is it allocates some memory that can work on either the CPU or GPU, and then just go ahead and compile and run that. Now, I'm not even going to add any actual GPU work yet. All I'm going to do is allocate the memory in a way that is legal to use on an NVIDIA GPU when we do add GPU workloads. So to go ahead and compile that code, and then I'm going to run it. Okay, so if we just look at the raw time that the code prints out, we now spent 0.39 seconds. You should compare that to the 0.02 seconds that it took to run before. Again, all I've done is change the memory allocation scheme. I haven't changed anything else. And because I can use this memory on either the CPU or the GPU, it should be perfectly fine to just allocate this memory and then use it on CPU only code. If I look at what happens now, if I look at my NVTX ranges, I see that 95% of my time is now spent in this allocate memory step. And so it dwarfs the compute bits. And if I look at how much time is spent in this one call to allocate memory, this is 411 milliseconds, right? This dwarfs the time spent in computation. And that 400 milliseconds largely is not actually how much time it takes to allocate the memory. It's largely telling you how much time it takes to initialize the GPU. And so it takes like half a second on most modern GPUs to warm up, at least NVIDIA GPUs, I should say. And so immediately what this is saying off the bat is if your application runs in less time than half a second, or like of order 1 second on the CPU, then you're not really going to be able to get any speed up by using GPUs, because just the time it takes to warm up the GPU will be as much time as it takes to run the application. And so you really need to be able to amortize that cost out by having a relatively long running application to compensate for that, half a second that you're spending warming up the GPU. Okay, so that's a long time. And really the only way to fix this problem is to make my problem bigger, right? This is essentially an unavoidable cost the first time you spin up CUDA in an application, and I can't really avoid that. So the only thing that I can do to solve the situation is to solve a bigger problem than the one that I was solving before, or one that runs longer. And this is a pretty common thing that you see when you're using GPUs for the first time. Often you need to solve a bigger problem than the one you were solving before. So in step 3 of this workflow, the only thing that I'm going to do is make the problem bigger. You can see
we have around 5 minutes now.
Yep. Thank you for the warning. So in step 3 of my thing, all I do is change the size of the grid from 64 squared to 2048 squared. This becomes a size that is more appropriate for running on a GPU. So then what I can do is I can go ahead and compile and run this step 3. So again, I'm just using the same nsys profile command that I've been using the whole time. I saw a question in the chat, is this really doing profiling or is it actually tracing the application? Yeah, Nsight Systems is essentially, for the most part, a tracing tool. So it's just collecting start and end timestamps of the activities. It does have a limited amount of sampling capabilities for collecting certain GPU metrics, which are known to be important. So you can get some information about like GPU floating point intensity, memory transfer to and from the GPU, that sort of thing. But for the most part, Nsight Systems is its bread and butter application is tracing. Okay, so I made the problem a lot bigger. As you can see, it's taking longer to run. That's expected. We increased the problem size by a factor of, well, whatever this is, and then it's that squared. So it should take a lot longer to run. The new runtime is 49 seconds. And if I look at my MVTX ranges, I now see that 64% of the time is spent in Jacobi step, 35% in swap data. And then now my allocate memory step only takes about 1% of the time. And so now, because we're spending a lot more time in compute than on the warm-up step, this is an appropriate thing that we could start tackling for a GPU workload. So in step 4, what we do is we run the Jacobi step on the GPU. And then in step 5, what we do is we run the swap kernel on the GPU. So I'm just going to jump to step 5, where we've ported both of these kernels to the GPU. And then show you what the new application timeline looks like. You can go through step 4 if you want to when you do the breakout session. So now, after we ported both of these kernels to the GPU, we are running for about 3.3 seconds, 3.2 seconds. And we still spend the vast majority of our time in Jacobi step, although now about 13% of the time is spent in allocate memory. And then in step 6, we get our first introduction to Nsight Compute. I'm just going to show you what the output of that tool looks like, just so you have a sense of what it's showing you, and then you can go through and read through the text, where I can do this in more detail in the breakout session. But basically, Nsight Compute collects a profile of this Jacobi kernel, and then it can give you a report on what's happening. And it's broken up into several sections. The one you're typically going to start with is called GPU speed of light. And that GPU speed of light section basically tells you what percentage of memory bandwidth did I get relative to the peak throughput of the memory subsystem, and then what percentage of compute throughput did I get relative to the peak compute throughput of the GPU. We use SM here because SM, a streaming multiprocessor, is the name of the compute units on the GPU. And so you can see that in this kernel, I'm getting a vanishingly small percentage of the peak throughput of the GPU. 2% of memory and less than 1% of compute. So clearly there's something to optimize in this kernel. And then you're going to go ahead and go through the steps of figuring out what those things are, and then step by step improve that, and then see what the tool shows you for improving that. So again, that was just a quick overview to how I think about using the tools. The step-by-step walkthrough goes into a little bit more detail, and I can show you some more of those in the breakout if you like, or you can just work on them on your own. But I hope you enjoyed this introduction to the Insight tools, and I'm happy for any brief questions. I guess I'm basically out of time, but you can ask me again in the breakout.
Okay, thank you so much, Max. It's a really nice overview, and I understand 35 minutes is not enough to introduce all the features of Insight computer and the system, right? So yeah, thank you for sharing the really nice example. So I put the Git repository the Max used in the Slack channel for NVIDIA. So if you have any questions to Max, please leave your question over there, and Max will watch the channel and interact with you. And also, after all the talk, we will have a breakout session, right? So we can continue this practice. So thanks so much, Max. I think Ray, are you ready to